Chapter 5 is the second law of the machinery. So the beginning of this is going to be reminiscent of Chapter 3. You remember a lot of little partial derivative relationships, and I think it's just messing with partial derivative relationships between things that you're not really expecting, like entropy and volume, and you're going to see these guys. So that's kind of where they're coming from, at least at the beginning it seems like. And they're starting with like internal energy is a function of entropy and volume, and then they get their total derivative expression, right? So internal energy is a function of entropy and volume. So then, right, and then we start, really you can play this game. I call it a game because I don't know what else you'd call it. You can play this game with any thermodynamic function. You can play it with internal energy, Gibbs energy, Helmholtz, enthalpy, and you can play this game where you pretty much just take the order of derivatives that really doesn't matter with these thermodynamic variables, and then you can end up getting some Maxwell relations. And these are just the most common ones, and that's why they're here. So I'll just, I guess, go by that. I mean, so here's our fundamental equation, and we just wrote the total derivative. So look what's in front of the ds, right? So that means the partial of internal energy with respect to entropy has to be temperature. Right? And then the same idea goes for this expression. It has to be negative p. Okay, and that's kind of what they're playing with. And like I said, you can play this game and get these Maxwell relations with all these thermodynamic functions. And I don't think you need to know this, but I have this, maybe it gives you some insight into stuff, like the second derivative of the internal energy. It doesn't matter whether you take it with respect to entropy or volume first. And out of that derivation, you get this. Or I think enthalpy is the next one. That was, yeah, with respect to P and S. And then the order doesn't matter for, what's that? Oh, it's Helmholtz. And with respect to what? With respect to T and V. And they're just playing around with that, and that's how they're getting. We're not going to mess with these derivations and things. It's just we're trying to give you an idea as to where this stuff is coming from. Right? With respect to T and P. So you're not going to be using any of this stuff, I don't think. You'll see how we're applying it in the homework. Okay, but there are some fundamental ideas that I think will be helpful, and that's really with the Gibbs energy, I think. Oh, here, I don't know what I have this here for. It's like I just threw it in. Maybe it's in the homework. Do you remember what pi t was?
Compressibility.
Internal pressure. Right. For a perfect gas, the internal energy was independent of volume, and that was one of the key ideas of that. I don't know why that's there. I don't remember the homework that well. Okay, and the first one problem? Oh, really? That's why it's in there. Okay.
Is it U is independent of volume?
Yeah, internal energy is independent of volume. Okay, so, but this is where I think the meat really starts. Why? Because Gibbs energy. If you remember your general physics, and you thought about work or trying to get some energy available to do work, we always thought of potential energy. At least that's kind of what I kind of think of. Like the gasoline in the engine. You think of the chemical potential energy. You know, there's always potential energy going into work. Well, with thermodynamics, that's the Gibbs energy. You don't. That's what they want you to think of. They don't want you to think of this idea of like in physics with potential energy. Now just it's analogous to think about Gibbs energy. So Gibbs energy is the energy available to do work. But it's under constant pressure and temperature. And that's why it's so common, I think, because the lab bench idea. You're under constant pressure and you're under constant temperature conditions. So when you're under these constant pressure and temperature conditions, this Gibbs energy is the way to go. And more insights into it is the Gibbs energy, that Gibbs function is what you minimize. It becomes minimized when blank is achieved. Chemical equilibrium. And that's kind of interesting, I think. So you minimize that function. In nature, Gibbs energy, you're always going to lower Gibbs energy. Think of it same as, again, it's analogous to the idea of physics and potential energy. You always think of minimizing the potential energy. That's the natural way that things go. If you have a ball on a table, well, that's not natural. It should end up even lower, right? So the same idea with thermodynamics and Gibbs energy. You try to think of, oh, we want to minimize Gibbs energy, and that's the natural way to go. Like a diamond. A diamond is one form of carbon. Well, graphite is another form of carbon. Graphite has a lower Gibbs energy than diamond. So naturally in your brain, you should think, okay, well, I want to go to minimum Gibbs energy, so I want to go from diamond to graphite. We have no idea how long it's going to take. This is thermodynamics, not kinetics, right? But it's going to be spontaneous. That's their talk. Properties of our Gibbs energy. What do we have here? So if you plot Gibbs energy and how it changes with respect to temperature, you get entropy. Keep pressure constant. Okay, so how does Gibbs energy change with temperature? It's supposed to be entropy. And here's the plot. See, they plotted Gibbs energy versus temperature. So that is exactly this slope, right? Because slopes are derivatives. Okay, partials because we have more than one variable, but we're keeping pressure constant. So how does the temperature change? How does Gibbs energy change with temperature? Here it's plotted out for gases, liquids, and solids. Does it make sense? So let's pick on Mel. Does it make which state has the highest slope? Has the grandest slope?
Yeah.
The gas. Does that make sense, Kevin?
Yes.
Why?
Because you're going
So you're staying as a gas the whole time. All they're doing is they're just changing the temperature and seeing what the Gibbs energy is. So it's almost like having a whole bunch of tables, because we're used to looking up the Gibbs energy information of oxygen gas. But that's always at one single temperature, 25 degrees Celsius, or 0 degrees Celsius, at some specific temperature. So you need a whole bunch of tables to get all these delta G values. You look them up. And they're just saying that, man, it's going to change most dramatically for a gas.
So it's already the hottest or whatever.
Gases exhibit the greatest entropy. That's why. And why are all these slopes negative?
Because as temperature increases, it's the T's on the bottom.
Because it's temperature, you're getting there. As the temperature increases, entropy is getting bigger. That means entropy is going to be positive or negative? Positive. So you'd think they'd all be going straight up, but it's negative S, that's why. Okay. Oh, can you answer a question again? What was the question?
I said, why is entropy negative, or why is the slope negative?
Because S is always positive as you're increasing temperature, right? As you're increasing temperature, entropy gets bigger, more states available. Entropy gets bigger, more states accessible. But that's why they have minus s. Because the negative sign takes that into account to make it go down. And then if we have plot Gibbs energy, how it changes with respect to pressure, keep temperature constant, well, that's going to be volume. Oh, before we, let me ask you this question. If we increase, before we go there, stick with this plot. Increase T, then what happens to the Gibbs energy?
Goes down.
Yeah, Gibbs energy goes down. Everybody agree? Right? Increase temperature, Gibbs energy goes down. So regardless of the table you look up, if you have higher temperatures, Gibbs energy better be going down. Okay, let's plot Gibbs energy with pressure. How to keep temperature constant. You get this slope, these plots for gas, liquid, and solid. Looks like it's not changing much for what two states? Liquid and solid, if at all. Why? Changing with respect to pressure. And they're trying to say that this change is really just volume. Does that make sense? It's a weird way of saying something that you already know.
It's kind of like, because if you have a liquid or a solid and you change the volume, the liquid or solid still occupies the same space. But if you have a gas and you increase the volume, that's going to increase the...
You're getting there. You're getting there. They're talking about not trying to... You get the volume. You're not changing the volume. You're changing the pressure, right? So you change the pressure. What's the result? The result is volume. So for solids and liquids, you get the volume. And is the volume changing?
Not much.
No. So in other words, is a solid or a liquid compressible? No. We already know that. They're not compressible. So you can apply as much pressure as you want, and they're not going to change volume. So it's just a roundabout way of saying, you know, solids and liquids are incompressible. But gases you can compress. So their effect on volume is going to be huge and dramatic. So that's what it's saying. So as you crank up the pressure, the Gibbs energy, it looks like it's going up, right? Okay. Gibbs Helmholtz equation. Is that where we're at? Yeah. I thought this was kind of weird. What was the symbol, Jeff, for Helmholtz? A. Well, in our Gibbs Helmholtz equation, do we have Helmholtz? No. So this guy Helmholtz must have just been instrumental in deriving this relationship, is all. Because the Helmholtz isn't even in there. So, well, what? Okay, we had G, and we talked about how you use this to minimize this function to achieve chemical equilibrium. It look kind of nice and that sort of thing. But if I think temperature is constant. So when I think we said that this was useful when you keep pressure constant. That was the idea. Pressure and temperature constant. And we use the Gibbs energy and all the ideas of how we can minimize it to achieve chemical equilibrium, and the idea of replacing in physics, replacing the idea of physics with, you know, potential energy. We're supposed to think of the same thing with Gibbs energy. But what I'm driving at here is, well, sometimes if the pressure isn't constant, and I remember reading somewhere, they're talking about like explosive chemistry or something like that. Sometimes it's much more useful if pressure's changing. Don't use G, use Helmholtz. So just that pressure can change. So it's, again, it's something that I don't see how you're not even going to have this in the homework. but I'm just trying to give you some idea as to why you have Helmholtz in the first place. You just pick the function that's the most convenient to use. And then, why do they have this in the first place? Well, the reason why they have this in the first place is they kind of skipped it, I think, because we're not going to derive this, but let's see, let me write it down if you derived it. Oh, it's supposed to be a little subscript. Let me write it down and then we'll say what it is. So yeah, you don't need this. But the point is that if you start with this Gibbs Helmholtz equation, you can get how the Gibbs energy changes with temperature. What's the Gibbs energy at a new temperature? Well, you can use this Gibbs Helmholtz equation to start you out and to derive a relationship to give you what the Gibbs energy would be at a new temperature. Okay, like see delta G at T1 or delta G at T2. So. This is kind of interesting, I think. To go from here, this expression, to this one. What changed?
Almost like you just distributed the derivative partial to
What changed?
The delta.
The delta. Right, look at that delta. If you put in a delta G, well, then you end up with a delta H over here. And that may not be so easy to see, so we might have to show that in the homework. But okay, I think we jumped ahead and we already talked about this. How gases and liquids, how solids and liquids aren't compressible, but gases are. Okay. So kind of that needs to be moved up. So the book, somewhere in the reading, the book hit this. And then they had this diagram, and then they jumped over here. And we're skipping, well, we didn't really skip it. We derived these relationships. You want to get the area under the curve, right? But the area under the curve is going to be an integral, but you can't pull V out of the integral, so you have to put nRT over P in for it, and then you derive and you get your natural log relationship with P like we did in the concept preview. So all they're trying to say is that, right, if you plot volume versus pressure, right, oh, good enough. You can't pull volume out of the integral because volume is dependent on pressure. So you have to plug in nRT over P in for it. And then we derive and we get what we did in the concept preview. So not really much there. Okay. So this first one, I thought I put hints on here, but I didn't because this first one isn't very easy. I have to add that. Hint. I was wondering how the heck I did it. We have to use the permuter and the inverter. Okay, so we gotta write down what this stuff was in the first place. Should have Gloriana do this, and she already.
I didn't like that problem.
All right, you pretty much just copied that from the solution manual, I bet.
Yeah, well, I learned from there.
Okay, so what is alpha and kappa T? Oh, I'm looking at our cheat sheet here. Yeah, negative 1 over v, partial of v with respect to p, constant t. And alpha is 1 over v, partial of v with respect to t.
Which cheat sheet are you looking at?
Oh,
All columns
yeah, the one with
Oh,
all
that
of this thing, with all the equations. Alpha, v with respect to constant p. Okay. So this, I wanted to give you that. This wasn't in your notes. Use the permuter and then the inverter. Okay, so remember what these are. I wrote down these. What were the permuter? Right? If you have the partial of x with respect to y at constant z, so this is the one where you kind of look at the dz's, they kind of cancel, is what you kind of think of it that way. That makes sense? That was our permuter. Oh, I forgot my subscripts, y and x. So that's our permuter. Our inverter was pretty much you just flip it. So I don't know how you do this without these hints. Okay. So we're supposed to start with this expression right here. We're supposed to start here. Right. So what did I start with? I think I used the permuter first, because I want to get these two. All right. So if I want to follow the permuter, so notice what's partial of x with respect to z. So I want to write right. So I'm trying to put that into here. Do you recognize it? So my x is going to be my x is going to be correspond with my p. My y will correspond with my t. Okay. So what's the z got to be then? V. Okay. So x we said was p. So the partial of p with respect to my z, and you said that was v. Right? Okay. dv, then dv on top. What goes on the bottom? dt.
That's negative in front, right?
Yeah, oh, I forgot the negative. Thank you. Forgot the negative. Okay. And p with respect to v, I have my t, v, t, p, right? That's the one that's missing. Okay. Now, do you see anything similar here? Look at this. V with respect to t. There's v with respect to t. So that don't mess with this. Leave it alone. Okay. This one, invert it. Invert it. Exactly. So we're going to, so that was the inverter. Sorry, not the inverter. That was the permuter. Now let's do the inverter. So write the inverter, but apply it to this one. Okay? Apply it to this one. Apply it to this partial derivative only. Leave this one alone. Go. Here's inverter. All right. So it's going to be 1 over partial of. All right. So look how x went to the bottom, y went up to the top.
So
dv over dp. Constant t. And we didn't mess with this term. Right? Okay.
No, it's just permuter.
Okay. Yeah, we're just kind of identifying. We take a look at the relation. Yeah, once you identify, yeah, good point. We said that z over here was v, right? But that's just applying this to the relationship. It's applying the permuter. And once you apply these, it starts all over again. So x could be something else now. Because now we're applying the inverter to, we can pick anything. So x could be anything. It's going to change on you. Okay, we're getting really close now, though. We're just missing the what?
1 over v.
The 1 over v's. So can't we just put in a 1 over v down here and put a 1 over v in there? Does that change anything? Oh, because it's top and bottom. There you go, we got it. So that's going to be, do you identify them? 1 over v with respect to p, negative. There's my kappa t, right? So this is going to be, kappa t is going to be where?
In the front.
In the front? Is it 1 over it, or is it on top? It's 1 over that, because identify kappa t, it's in the bottom. That's not a very good kappa. Right? And where's the alpha? On top. That's really alpha over kappa t. Okay, not a very fun problem. I don't know how you do it without being told permuter and then inverter. Unless you have the solution manual, right, Gloriana? Okay. 5.2. Suppose that 3 millimoles of nitrogen occupies 36 cubic centimeters, 300 Kelvin, expands to 60 cubic centimeters. Find delta G. Man, I don't know if I've given you what. Oh, you just handed it in, right? Didn't we just do this kind of thing on the concept previews? Because you want to know a delta G in terms of.
Or just, isn't it just nRT over V2 over V1?
Yeah, yeah, it's pretty much one of these, right? For it's relation number 2.
So that's just nRT over ln of V2 over
nRT ln V1 over V2.
It's on our sheet too.
It's on that. Oh, it is?
Our cheat, oh, the one in the back.
So 3 millimoles.
Really? I was that nice? I can't believe I was that nice.
At the bottom.
Here's the equation sheet for instructor 5. I don't have it in here.
Right there, we
Bottom
bottom
right.
gasity equation.
Right above B exercises. Bottom right above B exercises. Delta G equals nRT.
At the bottom.
Oh, I do have them in there. Well, I guess so. Okay, they're there. But know how to derive them, right? Know how to derive them. Now the milli, don't forget to put in what for the milli? 10 to the negative 3. Good. How about those volume units? Ah, dang, we got to convert them to cubic meters. Do you care?
Nah, because it's one.
They're going to cancel out on you. The time you can't play that game
Negative B
is with what units?
Pascals.
Well, P's. You could cancel. P's could be atmospheres. We don't care.
Oh,
Bars, millimeters of mercury.
Kelvins and temperature.
Temperature. Temperature is the one where that's going to mess you up. If you ever have a ratio of T1 over T2, they got to be in Kelvin. Yeah. Because that's an additive conversion, not a multiplicative conversion. Okay. 5.3. The change in Gibbs energy for a certain constant pressure process was found to fit this expression. Okay. Kelly, what does this mean again, this little slash J?
It's V1 over V2. I did it wrong. I did 36 over 60. I mean, I did 60.
Remember, this is his convention. This is Atkins' convention here. What'd that slash J mean? Alyssa, what'd that mean? It means that delta G has to be in joules. Right, it's not part of the equation, anything like that. It's just that delta G has to be in joules. T has to be in Kelvin. Okay? Find delta S for the process. So how is change in entropy related to Gibbs? I need a whole new equation sheet. I need to get a more modern one, up-to-date one here. Delta G equals H minus T delta S. Yeah, but I would keep a looking. That's not going to help us, because that's just going to be, we don't have all that stuff. How is Gibbs energy related to entropy, right? That's what we're looking at. Gibbs and entropy. Find another one.
Yes, dg over dt at constant p equals negative s, that one?
Yeah.
The one that we went over.
Partial of g with respect to t, constant p, negative s. Okay. The reason why this one works great is what's the one thing that's missing that we could directly apply this? In other words, directly apply this relation and get our answer. What's the one thing that's missing?
Delta s, right?
Delta. If we had a stinking delta symbol, see how this would be so straightforward? If you had a delta there, had a delta here, you would take, if you know what delta G is, if you know what it is, you take its, what?
Partial derivative?
Take its partial derivative with respect to t, and you will get delta s. So, and isn't that what we have? We have a Gibbs energy, and it has temperature in it. Just take the what derivative with respect to t,
Partial derivative.
and we will get delta s. If we can stick in those deltas. right? That's the question. If it is, if true, then we can write our answer right away. Take the partial of this guy. Negative 85.4. What would you end up with as an answer? If you took the derivative with respect to temperature.
It's going to be like the same thing, right? Is that a T right there? Is that 36?
That's what I was asking when.
That's 36.5 T?
That's Alyssa knows. What? It's T has to be in Kelvin. That's all that slash K means. So you take the derivative of that with respect to T, you just get 36.5. All you get is 36.5. Okay, but can we do that? Can we do that? Yeah, yeah. So we should probably show that you can. We probably should show that you can. Otherwise.
And is that in joules? Yeah.
And I know it's in joules. How do I know it's in joules?
Delta G's in joules.
Because delta G's in joules. That's all that slash J meant. Okay. So if we erase these guys, we would have, now I can start over. So if I said, I don't know, put a little F here, put a little F there. That part should make sense, right? There's really no argument there, I don't think. So delta G then, G final minus G initial, right? Okay. So that should really be, let's see. We have a negative sign there, though. Plus SI. Am I jumping too far ahead? Right, because
Putting the deltas in and then distributing the negative.
yeah, that negative sign messes up. But that's why it looks odd on this side. So what I'm trying to show is that if I take the partial with respect to t, how did I do this? Maybe we're starting out, maybe if we started out here, start out where it's easier. Partial delta G with respect to t equals negative delta S. So that'd be partial of G final minus G initial with respect to t. So then I'd have the partial of GF with respect to T minus the partial of GI with respect to T. So then, sorry, I lost my SI. So that would be Yeah, that should work.
Hmm.
Do you see it?
Yeah.
It works. It's just easier if you start out with your answer than starting the other way. 'Cause all I did is I pulled out the partial with respect to t there. Okay, so it's safe. It's safe. So these two I don't think are so bad. This is calculate, look how it says calculate the final pressure. Well, that's just jumping to that relationship. You have to get rid of the natural log, right? Get P2. Well, how do you get rid of natural log, Shelby?
E.
Raise everything to the e power. Yeah,
Well,
that's
this
not so
one,
bad.
You don't know delta G, right? So how do you get delta G first? You gotta find entropy. Do you do that by
Can't
the
you
same
use
thing
that
you just did?
equation for entropy?
Yeah, the same
Yeah,
thing
they,
you just
they
did.
told you. So
Yeah,
they told you the entropy.
but then how do you get the final pressure?
Well, the final pressure is using that expression,
The delta G one?
the delta G expression.
But we have to get delta G first, right?
Yeah, you know what entropy is, so you can calculate your delta G.
With that last equation that we just used?
Yeah,
Yeah, okay.
that's what I would do.
So it's the
I think I calculated my P.
I just came in and still occurred. I was like, just still when I actually closed, like, just come back. Like, I didn't know this was. That's why.
Okay.
So just delta G for probably 25 potential. Or you want that? Yeah, that's the stuff.
So 5
Right there. Would you, is this delta G is equal to negative delta?
So I would use the delta S relationship. Remember we have how these in our concept previews. What was it? Delta S was NR P2 over P1.
Is it NRT?
I don't remember. I don't remember. But remember that. You remember where I'm coming from? That those delta S relationships in our concept preview. That was like chapter 4, I think. So that's where you start, I would think, and that's how you could find the final pressure.
And how do you calculate that?
And then you calculate your P2. And then once you know your P2, you can use the concept preview chapter 5 expression to get your delta G, because now you know what both P's are. Does that make sense? Mel, did you follow that? So use the chapter 4 concept preview first, and then the chapter 5 concept preview.
So delta S equals NRT
Okay.
ln P1 over P2.
Yeah.
Delta S was what? NR?
NRT ln P1 over P2.
Oh, what's P1 over P? Yeah, that's right, because they're inverse of volume.
I don't know what I did with that.
We're out of time. But you can, I think your homework will be pretty
Yeah, we just
straightforward.
get